Hello, we are Sohan Rudra, Rakshit Verma, Manan Khaneja, and Rajdeep, and we will be talking about anytime heuristic search in this presentation. Let's talk about the terms first. An anytime algorithm can return a valid solution to a problem even if it is interrupted before it ends. A heuristic is some information which can provide domain knowledge to the search problem, which could facilitate fast solution discovery. Search is a step-by-step procedure which can generate a sequence of states and actions from start to the goal nodes if such a solution exists. So why anytime? The ability of having a possible solution at each time step is essential in areas which have a propensity towards sudden changes. An optimal planning algorithm usually takes a huge amount of node expansions, and if a sudden change occurs to the graph, then the current solution will be rendered moot. Some of the possible environments where fast replanning is crucial are as follows. Partially observable or rapidly changing environments, noisy states, and imperfect execution plans are some of the areas where having a possible solution is important. Moving on to search. Now let us look at the formalism of search. First, we have the terminology. In the following terminology, X is the state space, U of X is the action space, X subscript G are the goal states, F of X comma U is the state transition function, G of X is the path cost from start node to a node X, C U comma V is the cost of path between node U and V, and H of X is the heuristic function. Moving on to the formulation, we first initialize a non-empty state space X, that is the state of all possible states. Starting off with an initial state X of I and a goal state X of G, the state transition function is defined using which the entire graph is created. Over this graph, a possible search algorithm can work. Now let us talk a bit about formulation of the heuristic. In this context, we need a function that ranks the alternative states in a search algorithm based on the available domain knowledge. For any heuristic, it is essential that it satisfies two criteria: admissibility and consistency criteria. A heuristic is admissible if it never overestimates the true cost of the goal. A heuristic is consistent if, when going from neighboring nodes, let's say A to B, the heuristic difference or the step cost never overestimates the actual step cost. That is, the heuristic function follows the triangle inequality.
A-star search algorithm is a graph traverser algorithm that helps in determining the most optimal path. When compared to Dijkstra, it achieves better performance by using heuristics to guide its search. For a given node or a square in a grid, we choose the next one for the minimum value of f. F comprises of two components. G gives the movement cost from the starting point to that point, while H is an estimate of the movement cost from the given point to the final destination. Looking at the algorithm, we start by initializing the open and the closed lists and put the starting node in the open list. The next step is initializing the cost and the heuristic functions for every state. From there, the computation moves towards the inner loop. We keep running the search until the goal node has been expanded, that is, put into the closed list. First step is choosing a node with the minimum f value from the priority queue. Then using the state transition function and the action set, we find the set of possible next states and put them into the variable sug. We iterate over the successors. If we find a successor which has already been expanded, then we let it be. If the successor is not in the closed list, then we check if a better path can be found to that successor, in this case X from that x, that is the previous best path. This happens, we update the cost and finally place the successor into the open list, and the search keeps on progressing until we reach the goal. Looking at the properties of A star, it is guaranteed to return an optimal path, that is, the path from the start to goal will have the least path cost. Secondly, it performs minimal number of state expansions required to guarantee optimality. In case of weighted A star, the primary difference from the A star algorithm is the introduction of the epsilon in the node selection function. The value of epsilon chosen is always greater than 1. Now, how does the weighted heuristic approach help? In case of weighted A star, more emphasis is given for moving towards the goal at the cost of optimality. As you can see, more nodes are expanded towards the goal and the path is found in fewer node expansions. An epsilon consistent heuristic will overestimate the actual cost by a factor of epsilon, which will in turn cause the final cost to be epsilon suboptimal. As we keep on decreasing the value of epsilon to 1, the weighted A star reverts back to the original A star algorithm.
Now we will move on to the anytime search algorithm. Before diving into the exact algorithm for anytime A star, which has a number of different variants, we will try to see how the weighted A star can naively give us a possible way to perform anytime search. Shown below are 3 graphs. On each of these 3 graphs, a different version of the weighted A star search has been run. Moving from the left to right, you can see the weights of the weighted A star as decreasing, starting from epsilon 2.5 to 1. So this shows an interesting trend in the number of node expansions as well as the quality of solutions. The number of node expansions starting from the extreme left hand side is 13, moving on to 15 and finally to 20. And the solution moves starting from 11, goes on to 11 again, and then finally to 10. This shows that as the weight is decreased, the solution becomes more and more optimal, while the number of node expansions increase. Hence, anytime search can be interpreted as iteratively running the weighted A star algorithm with the decreasing weight. As time progresses, the decreasing weight will push the solution towards the optimal. Anytime search in this way iteratively updates a course solution and makes it finer and finer as the time progresses. Anytime search algorithms have some key requirements. First, you need a non-admissible heuristic to facilitate weighted A star search. Then there has to be a provision to keep the search in a continuous state even when a solution has been found. And finally, you would also require an admissible heuristic for pruning the search space and also for detecting when to stop the search entirely if an optimal solution has been found. Next, we will move on to the algorithm. In the initialization phase, you can see we have 2 different sets, the open set and the closed set, similar to A star. For every state, the weights are initialized, the start state having the weight 0, and moving on, the rest of the other states having weight infinity. Additionally, each state also needs to be initialized with a given heuristic value, and as we had 2 different heuristic functions, each state will have 2 different heuristic values. And finally, an additional item needs to be initialized, which is the intermediate solution. This is a variable, in this case n, which will store the intermediate solution when found. Next, we will see the entry condition of the loop. So the search continues while the open list still has nodes and if the interrupt hasn't been called yet. The procedure will start with selection of a new node from the open list given by this particular equation, and it will select that node based on the non-admissible heuristic. Next, there is a check in place which prevents the node having a value greater than the previously found solution for the f function to be expanded. which means a node having the f value higher than the previously found solution will not be expanded, as that will imply that it will lead to a worse path that was from the one found in the previous iteration. The given node is inserted into the closed list, then we will move into the inner loop. In the first line you can see we find the immediate successors of the given node, and then for each of these successors, such that the value of the function as shown here is less than the previously found solution's f value. This ensures that even in the successor nodes, no node is put into the open list if it has a value which is worse than the previously found solution. Next, a check is in place to see if the node is goal node, it will update its f value and the g value. It will initialize the intermediate solution with x prime. Unlike A star, we check if a node is present in the closed list also, because a node previously expanded in a different iteration of the search could also be possibly updated if we have found a better solution reaching to that particular node. Then if the new path, which is the path from the given expanded node x to the node x prime, has a shorter length than the cost of the x prime node, we will update the costs accordingly for the cost function, also for the heuristic function and for the non-admissible heuristic function. If the node was already in the closed list, we will pop that out of there and place it into the open list once again. And if a completely new node is found, procedure similar to the A star of updating the cost function, and the two different f functions are performed and the node is placed into the open list. Finally, if the interrupt has been called or the search finishes, we return the goal node along with a given error value. This error value is the measure of the suboptimality of the solution. So if the open list is completely empty, the error will be 0, as it means that the optimal solution has been found. If the open list is not empty, the error would be the difference between the current solution's f value and the minimum node's f value from the open list. Anytime A star also has some important properties. Firstly, it always terminates. If it continues to run, the last solution will always be optimal. Anytime A star refines the upper and lower bounds to cost of the solution, and these bounds in turn get close to each other as the search progresses.
Now let us look at some of the use cases, some examples of anytime heuristic search. The first one is the sliding puzzle problem. So a sliding puzzle is a combination puzzle that challenges a player to slide pieces along certain routes to establish a certain end configuration. So as we can see in the GIF, we are allowed to move the pieces in only vertical or horizontal direction where the place is empty. It is often used as a traditional benchmark, and anytime algorithm has the capability to solve this problem efficiently. The solution quality improves as a function of computation time. So in the first graph, we can see that a weight of 1.3 seems to result in the best overall performance among these three weights, although it does not dominate the other performance profiles for all running times. So it is the performance profiles for anytime WA star using three different weights averaged over all instances of the 8 puzzle. By all instances, we mean all possible starting states and a fixed goal state. The goal state here has the blank in the upper left corner and the tiles arranged in numerical order from left to right and then top to bottom. And we are using Manhattan distance heuristic here. Figure 1b shows how many nodes anytime WA star stores and expands before it converges to an optimal solution using different weights. Again, by converges to an optimal solution, we mean that the lower and upper bounds meet and the algorithm has proved that the solution is optimal. So these toy problem, anytime algorithm is able to solve them very efficiently. Next is the problem of dynamic planning. In this case, we are trying to find a path through a maze, and the maze is changing as the car is moving. So the car uses sensors to see obstacles, and eventually the car is able to plan complex routes to the goal. The blue path here, which we can see, it represents the global path, but the maze is changing as the car is moving. So planning has to be done very rapidly. Like we see that the node is cut off, so the car moves back and then finds an alternative path. It is replanning at the moment and making decisions very quickly. That is why anytime A star searches are helpful in these scenarios, as the planning is repeated every time the robot cancels the previous plan. So the graphs in this type of problems are dynamic, and we use anytime algorithms because they are useful for problem solving under varying or uncertain time constraints, as they have a solution ready whenever they are stopped. The green spot is the goal position. The car not only has to reach the point, but it also has to attain a given particular position. That is, the car has to face the bottom left corner in this case. Next is robotic motion planning. So robotic motion planning or motion planning, path planning, is a problem in which we find a sequence of valid configurations that moves the object from source to destination. Robotics planning has a bigger global path like a global waypoint, and there is a local planner which plans like A star or AR A star, anytime repairing A star, satisfying all the possible constraints and trying to reach towards the goal. The graphs which are made, they change dynamically with the environment, and the environmental representation may not always be accurate. Hence we need fast replanning, and this is the reason again why we need anytime algorithms. So at bottom left we can see that optimal 4D search with A star takes 25 seconds, whereas 4D search with AR A star takes only 0.6 seconds to reach the state, where epsilon is 2.5, and if epsilon becomes 1, then it again becomes A star only. So these were some of the examples, and these are the resources that we have used. Thank you.